Today, we want to look at exponential functions and percent change. If you would recall, last time we looked at the function where y is 36 when x is 0, and y is multiplied by 0.76 every 6 units. We have to be able to translate a multiplier into a percent change, increasing or decreasing by a percent. So if we take the 100 and take 100 and subtract 76%, that means we're left with 24%. And so we could describe what's going on in this function by saying y is 36 when x equals 0, and y is decreasing by 24% every 6 units. So here's a description of what's going on every 6 units. We might want to know what's going on every 1 unit. So to calculate, to sum up what happened when we want to calculate what's happening every 1 unit, we take the 0.76 and raise to the 1 over 6 power. Remember that this is a description about how things are changing, so it's the 36 isn't going to matter because we're going to divide out the 36 in both cases, in whatever case we choose. So we just care about the 0.76 to the 1 over 6, and that's what'll be happening that'll be the percent change or the multiplier for delta x of 1. 0.76 to the 1 over 6 power is 0.955. Once again, we don't care about the 0.7 the 36 part. We take 0.76 to the 1 over 6, and it makes me realize that I've used 6 way too much in this problem. It makes a very sibilant problem. 0.76 to the 1 over 6 is a 0.955 and some other stuff, but let's round it to 0.955. So I can write this equation, 0.76 to the x over 6, as 36 times 0.955 to the x. And I can translate our multiplier into a percent change by subtracting from 100%. So 100% minus 95.5% is 4.5%. So y equals 36 when x equals 0, and y is decreasing by 4.5% every unit. So the question is, why can't we just take the 24 and divide it by 6? Why is it not 4% every unit? Why is it 4.5% every unit? Why do we need to be taking off more? So to talk our way through it, if we'd only take off 4% of what we start with, then we have less. So if the amount is decreasing. So after 1 unit, if we took off 4%, let's start off with 100. 36 was a bad choice to start with. But if I start with 100 and subtract 4%, now I have 96. Now if I subtract 4% again, I'm going to be subtracting less than I subtracted before. So before I subtracted 4% of 100, so I subtracted 4. Now I take 96 and subtract 4% of 96. So the amount I'm subtracting is only 3.84%. So where I subtracted 4 from 100, I only subtract 3.84 from 96. So now the 92.16, if I subtract 4% of 92.16, I'm at 88.47. What I've subtracted is 4% of 92.16. So I've only subtracted 3.68. So because the amount is decreasing and the change is based on a percent, the amount that we're subtracting is decreasing as well. That's why I have to subtract 4.5% per unit to take into account the amount decreasing by a percent. Any questions? Now I was just kind of talking our way through it. Hold on one moment. So we have to decrease by a little bit more than 4% because the amount that, because we're calculating the amount of decrease with multiplication and the amount, or with a percent. And so the amount that we subtract is decreasing each time. So we have to start off with a little bit more. The same thing will happen if we have a function that is increasing. So if we have a function that is, let's suppose that we have a function that is going to double every 10 units. Let's suppose that, let's just write it in the way that we normally write things. Let's suppose that y is equal to 100 when x equals 0. And let's suppose that y is going to be multiplied by 2 every 8 units. So we might see this phrase differently. Multiply by 2, we might see this as doubling every 8 units. So we might see this as y will double every 8 units. Or we might see y is increasing by 100%. All different ways of describing multiplying by 2. We think of the 200 and we subtract the 200 from 100, we'll get the 100. So it's increasing by 100%. So y is 100 when x is 0 and y is multiplied by 2 every 8 units. That will give us a function. Let's turn this into a function that we can work with. Y is equal to, we start off with 100 and we're going to multiply by 2 a bunch of times. So we'll raise this to an exponent. And the step size is 8, so we'll raise this to the x divided by 8. So here's an equation that says y is 100 when x is 0, and y is multiplied by 2 every 8 units. Now that we have an equation of this form, we can ask what's happening every 1 unit. So to do that, we'll take just this part, 2 to the 1 over 8. We don't care about where it starts, we care about how things are changing. So I take 2 and raise that to the 1 over 8 power. Grab my calculating machine. 2 to the 1 over 8 is 1.09, we'll call it 1.0905, so 1.091. So that means I can rewrite my equation as, instead of saying y equals 100 times 2 to the x over 8, I can write this as y equals 100 times 1.091 to the x. Here's a description that's going with every 1 unit rather than every 8 units. If I take the 1.091 and subtract 100 from it, I take the 109.1 and subtract 100%, I get 9.1. So I could write another description of this function by saying y equals 100 when x equals 0, and y is increasing by 9.1% every unit. So these are all ways of describing the same increase. Y is equal to 100 when x is 0, and y is multiplied by 2 every 8 units is the same as y is equal to 100 when x equals 0, and y is increasing by 9.1% every 1 unit. And we should notice that this is not the same as taking the 100 divided by 8. 100 divided by 8 is not 9.1. But when a function increases by 9.1%, 9.1% in the next step will be a bigger amount. So I don't have to split it up evenly. Any questions? Now we can take a look at this. Oh, I didn't have my calculator set up. Uh-oh. So if we switch over to our graphing calculator and take a look at 100 times 2 to the x over 8 and compare that to y equals 100, that's just a flat line, but now times 1.091 to the x, notice that we see the same graph. It's going to be a little bit different if we zoom in real close. They'll start to separate. See how the line goes a little bit purple? But that's because things have been rounded off. So if we can see that there's getting a little bit of separation because it's been rounded off. But if I go in here to the 1.091 and include more decimal places, so 1.09, I change it to 0.5. Now they're closer until we zoom in some more. Now they're close until we zoom in some more. And then if I add more decimals, 0.05077, now they're even closer. And I have to zoom in really close. So here we are at negative 23.046, and at this side, negative 23.045. So things are very close together. And I can go past my calculator's ability to calculate things. Meanwhile, let's zoom in on Desmos. And to get separation, the same separation we had before, Desmos is like, well, I'm not even going to tell you how close we are here. Let's drop down. Let's find out. That's going to be too far. Because I zoomed in so much. So we have two different ways of describing what's going on. It's important that we be able to do these calculations. There we go. It's important to be able to do these calculations because they sound pretty different. If I say, well, this quantity is going to increase by 9.1% every unit, that might be less impactful than saying something is going to double every 8 units. Let's suppose I described what's going on. This is one of the reasons that we hear things like 9.1%, and sometimes 9.1% doesn't seem like a lot, and sometimes 9.1% seems like a lot. the value of this investment will double or will increase by 9.1% every year. What that means is that the value of the investment will double every 8 years. So $100,000 now, if it's going to grow by 9%, will be $200,000 in 8 years, if you can get it to be 9.1% the whole 8 years. So it's important to understand that these two descriptions represent the same amount, and we can translate between one and the other, but it's not as simple as dividing. So if we don't want people to be frightened, we might say, well, there are 100 zombies today, and it's projected that the number of zombies will increase by 9.1% per day. What that means is that in 8 days, there's going to be 200 zombies. The population of zombies will double every 8 days. So in 8 days, there'll be 200 zombies. In 16 days from now, there'll be 400, and exponential functions grow very fast. We just look at a pattern of multiplying by 2. At 8 days, there'll be 200. At 16 days, it'll be at 400. At 24 days, a little over 3 weeks out, we'll be at 800. And in a month, it'll have grown by 16 times. So this is just 9.1% per unit, but that will increase by 16 times. 9.1% per day will increase by 16 times over a month. One thing to note is that we want to be familiar with how exponential functions are described. But the other thing that needs to go along with this is a lot of times we say something is growing exponentially when we mean something is growing quickly. So just because something is growing quickly, we do not want to say that it's growing exponentially. When we say growing quickly, we're being vague and just descriptive. But when we say a quantity is growing exponentially, we mean something very specific. It's increasing with multiplication. There's some percent change that we can measure. So don't say exponential because you mean something is growing exponentially when you mean something is growing fast because you think you sound fancy by saying exponential. You're trying to use big words when smaller words would suffice. So it's like a double negative. You're not only sounding just trying to sound fancy. It shows that you're trying to sound fancy. And you never want it to just look like you're trying to sound fancy. You know what I mean? So don't land yourself on confidently incorrect or whatever subreddit might refer to people trying to inflate their language. All right. Let's talk about where exponential functions and polynomials will collide. Get away from patterns for a second. So we're going to set up a simple scenario. Let's suppose we are going to invest $50 something simple like $50 into an account that earns. Now this is going to be a lot of interest to keep the numbers simple. That will earn 1% each month. This is very rapid growth, but I didn't want to use a fraction of a percent at this point. So notice that 1% per month, that we're going to multiply by 1.01. So if I multiply by 1.01 12 times, that will increase by, multiply by 1.1268, or increase by 12.68% per year. So that will earn 1% each month. Here we're saying y equals 50 when x equals 0. And we're saying that y is increasing by 1% each unit. So even though this is phrased in some context, I can translate it into a description of an exponential function. When we say y is increasing by 1% every 1 unit, we could translate this into multiplication by saying y is multiplied by 1.01 every 1 unit. We can turn this into a function. We could say that y is equal to 50 times 1.01 to the x. I'm going to say to the x since it's every 1 unit. Now we have some stuff to work with. We've taken our simple scenario and translated into math. What are we going to multiply by every year? If it's 1% every month, what does that mean each year? A lot of times we talk about things in terms of annual growth. If we're thinking of a long-term investment, we should think of annual growth. And if I take 1.01 every 1 unit, we're going to multiply by 1.01 12 times. So multiply by 1.01 12 times. We know that repeated multiplication is exponents. So I'll take 1.01 and raise that to the 12th power. 1.01 to the 12th power is a 1.1268. And we can turn that into a percent by subtracting off the 100. So that's increasing by 12.68% every year. So it's a little more than just 12% because the 1% happens after the first month. So now we have a little bit more going into the second month. So 1% of $50 is not the same as 1% of $50 plus another 1% of $50. So if y is equal to the amount of money that we have would be 50 times 1.01 to the 12th power. So the amount in the account would be 50 times 1.01 to the 12th power, 56.34. So that's how much we would have. That's an increase of 12.68% rather than just 12%. Because the amount that we get interest on the interest, the amount of increase is going to increase. So if we stretch this out to a very long time, this is we'll have 5634 after 1 year. How much will we have after a very long time? Let's suppose we want to know what's happening after 20 years. Well, 20 years times 12 months per year is 240 months. So I have 50 times 1.01 to the 240th. So let's try that. Same thing, but instead of 12, now I have 240. So 544.63. Doesn't seem like a lot, but this is all just from $50. $50 20 years ago. The question is what does 1% per month beat inflation or not? I said earlier that it's a mistake to refer to exponential growth as just fast growth. Exponential growth is eventually fast. Notice in after 12 months, it's only gone up, our investment has gone up by $6.34. Not really noticeable. But eventually, we start seeing much faster growth. What about after 30 years? That would be 50 times 1.01 to the 30 years, which is 360 months. So now, the first 20 years, we spent going from $50 to $544. The next 10 years went from $544 to $1,797. So that was just in 10 years. And then after 40 years, I forgot to do 10 years. Oh well. Oops. So it spends 20 years getting multiplied by about 11 from 50 to 500. But then in the next 10 years, we go from 544 to 1797. So in those 10 years, it tripled again. And then in those next 10 years, it tripled again. Notice that in these 10-year gaps, 1797 and 48 divided by 544.63. If I look at it in terms of multiplication, we're multiplying by 3.3. 5932.39 divided by the 1797.48 is another multiplier of 3.03. So what we're seeing is that 1% every 1 month is 12.68% every 1 year, and that's a multiplier of 3.03 every 10 years. $3.30 every 10 years. And the same thing happened here, multiplied by 3.30 every 10 years. Or an increase of 230%. Every 10 years. Any questions? To sum up, especially when we're talking about investments like this, not that I'm not qualified to give investment advice, but I'm not really doing anything but dispensing kind of common wisdom based on the numbers. So, unsolicited, unprofessional financial advice. Time is the biggest asset that you have as far as investments go. Notice that this option here after 40 years is kind of off the table for me. I'm going to be 50, so I'm not really concerned with what's going on when I'm 90. I'm not really, so although this sounds really good, just put 50 away now, then when I'm 90, I'll have almost $6,000. That's not that useful to me. My family history says I'm not going to probably not going to make it to 90. But if y'all are 20 right now, this is when you're 60. And so you might be thinking you can't afford $50, but maybe you can't afford not to sacrifice that $50. You know what I mean? Now, this is also not enough to live on in 40 years. Just a wild prediction. Because in 40 years, it's going to be a post-apocalyptic hellscape, and we're going to be using bottle caps if Bethesda is correct. But if we manage to avoid that, and yet there's still money, first of all, I'll be kind of amazed. And second of all, that means that we should start now when 40 years can be a possibility. Because doing this for 10 years is so-so, but we're multiplying by 3.3 every 10 years. So let's multiply by 3.3 as many times as we can. At the beginning of this page, I said what happens when polynomials come into it. So that's going to be, what happens if instead of 50 once, what if we do 50 every month? So what we want to do next is take this concept of simple interest that we're applying to just a one-time input of $50. And what if that $50 not just went in 1 month, it went in every month for the next 40 years? Or what if we don't have $50 now, so we do $10 a month, or even just $5 a month? How do those things build up over time? Remember, this is exponential functions and how time is important in an exponential function. Linear functions don't care. Linear functions, it's like fixed amount the whole time. In 20 years, if something's growing by $100 a month, in 20 years, it's still only $100 a month. But exponential functions, time is a big factor. All right, that's going to do it for today. Tomorrow, we'll see about where polynomials come in and what happens if we do $50 every month. And then we're going to start playing with those numbers. Change the rate of return, change the amount of time, change the amount we invest every month. That's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.